Welcome to the second part of machine learning lectures. How is the midterm grade? Okay? Yeah, I haven't done any carving yet, so I can do it right now or maybe at the end, whatever you like. Let me know. Okay? You can send me message which one you prefer, but it doesn't matter at the end of the day. That's what I said earlier, that's what I'm saying right now. Okay? So don't worry about it. So we will try to make the second midterm less, at least in terms of volume of work you need to do. So I don't know whether it will be easier. I mean, that's a judgment that you have to make, but I'll try to make it less content for the next one. Okay? But again, you have to, I think one concern that people said like, hey, I did the assignment and I didn't get the same type of questions. That may happen because we are testing your concepts in the midterm. We are not asking you to implement something or make something work. It's mainly about your conceptual understanding of the basic machine learning topics. All right? Yeah, so without further delay, I'll start today's lecture. And we are going to talk about kernels today. So how many of you have heard about kernels? There are two types of kernels, at least in computer science. How many of you know about two types of kernels? What are they? Yeah?
In operating systems, there's a kernel that loads the operating system.
I mean, the core of the operating system is called a kernel, right? Right. So kernel basically means kind of a core. But in machine learning, it means a little, completely something different. Okay? It essentially means a function that you can represent as a legal dot product. That is very different, right? So just to know, like this kernel has nothing to do with the OS kernel. Okay? All right. How many of you remember perceptron? Who has never heard about the term perceptron? Like I have no idea what it is. Okay, that's good. So today we are going to start from perceptron, and we are going to say, we know a lot of limitations about perceptron. We will try to see what we can do about it, right? That's the idea. What is the major limitation of perceptron?
Linearly separable data.
Linearly separable data is a problem?
Is a requirement.
Is a requirement, that's the problem. Okay, what else? Well, let's start with that big problem, right? We have perceptron, simple algorithm, just do dot product and have something interesting as a classifier, but it only works when there is a linearly separable data. And that is a problem. And we said like, and we kind of see that real life data is not linearly separable most of the time. We need something non-linear. That's where kernels come in, okay? So I'll go pretty quickly for the first few slides because this is just a recap of perceptron, okay? So quick recap, we had a perceptron model like this, which is an online algorithm. You get an example, you make a prediction by dot product, and then you see whether you made a mistake or not. And then you actually made some corrections to the decision plane, right? So this is how it looked. So it was essentially the algorithm where we add the instance x if we make a mistake on the positive case, or we subtract the instance x if we make a mistake on a negative example, right? And so essentially, W is getting weighted by a linear combination of the mistaken examples, where AI1 is positive 1 if it is a positive mistake. AI1 is AI is 0 if there is no mistake, and if AI is -1 if it's a negative mistake, right? That's what the update rule was. And if you take this WT with a new X, this is what it looks like, right? Essentially, you are taking a linear combination of multiple dot products, right? The new dot product is essentially a linear combination of multiple dot products. Now, we talked about this margin idea, and we talked about why this margin is important, because we want to maximize this margin when we define a plane, right? And the definition was, given a plane, given a point, look at the distance of x1 from that plane in the perpendicular direction. Whatever that is, that defines the margin, right? Then we said, if there are a set of points, then the minimum distance among those set of points define the margin of those set of points. And next, when we said that if there is no W defined, fixed W, just the points, then among all the possible Ws, the W that maximizes the minimum margin. So it's a minimax problem. We already defined all these terms. So that maximizes the minimum margin is actually defined as the margin of a set of points, right? And this is the definition of margin we are going to use in our future lectures, as well as we move forward to support vector machines. We also proved this. We said if data is linearly separable by margin gamma, in order to prove this theorem, we defined gamma, and then we showed that and if all the points are within this radius of R, then the perceptron makes less than this number of mistakes. And by this time, it already converges. You get a solution, right? We theoretically proved it. All right. Okay, so now comes our topic. So far we have been talking about linearly separable data sets, and we want to talk about nonlinear cases. For example, look at these two images, and we want to predict with a perceptron that whether the picture is of a male or a female person, right? If I just take the pixel values, do a dot product, do you think that will work? How many of you think that will work? No. How many of you think it will not work? Why do you think it will not work? Yes?
I think it would have to take some into account, like not just the pixels, but the positioning of the pixels.
Okay. So the whole point is, if I define a linear space with the pixel values, most likely it will not be linearly separable. That's why the dot product is not going to solve us. It's more complicated than that. It's a complicated problem. It's a non-linear problem, most likely. And that is true. Image classification is not very easy, because when you are classifying images, think about this. How do you know it's a man or a male person? Just by looking at it? But your brain is doing a lot of pattern recognition calculations in your mind, right? You are looking at essential features that defines a male person versus a female person. For example, well, her hair is not that long here as well, but there are definitely something you can figure out. Still, the hairstyles can still tell you something about it, right? What else? Does she have a band here? Maybe. Yeah. Yeah, the hairstyle seems to be the most important feature here, but still, like, there are features at different abstract levels, like exact pixel level, at a zone region level, where you have maybe eyebrows as well. I don't know. But the point is, it's not straightforward. There are complicated features that we need to construct. To really, it's not just the pixel values that you take and that's it. You need to combine all those pixel values because those are the raw features you have, raw data you have. You need to create more complicated features that can actually capture all those properties. So basically, you need to combine all those pixel values into complex features. And maybe if you define that complex feature, then the problem becomes linearly separable. Not at the pixel value level, but if you define those features, hairstyle and all those features, let's say we can compute a number. That will make it linearly separable. Oh, males' hairstyle numbers are here and females' like hairstyle numbers are here. Of course, this is not that straightforward, but it's just an idea, right? Right now, the pixel doesn't give you a value for a hairstyle. Okay? All right. What we do for this? Yes. So we can learn more complex functions like a decision tree, neural networks. Decision tree is indeed not a linear classifier, right? Remember? It can be non-linear. But yeah, there are cases where decision tree is also not good because it cannot really handle optimally the continuous variables, right? It has to be discretized. So there is some loss in the process. But images are continuous values kind of thing, right? So the other idea is to use a kernel. And kernels essentially create those complex features. That's the whole idea. It basically computes complex features at a high dimensional space, hoping that it will capture those more complex features like hairstyle and all that. It doesn't really compute a hairstyle feature. It computes some high dimensional feature with a hope that their combination can define those features. All right? We could do neural networks because neural networks are universal approximators which can approximate any function if there exists one. And we could combine kernels with deep networks as well. So these are many, many different techniques you can have. And we have already covered decision trees in our course. We are going to teach kernels. We are going to teach neural networks as well as we are going to teach support vector machines. So that's kind of the scope of this course. Questions so far? Good. So the question is, what is a kernel? So the kernel is a legal definition of a dot product. What is legal here? The point is, so first of all, kernel is defined between 2 points, x and y or z, let's say. So kernel has to be between 2 data points. And it has to relate to their it has to relate it to their dot product. How? It has to be such that this function can be written as a dot product of a transformation of x and the same transformation of z. That is the definition. If this doesn't hold, that is not a valid kernel. I mean, I can write many, many different functions for x and z, right? But not all of them, you can, not for all of them, you can find a unique phi. It doesn't have to be even unique, at least one phi, where the phi transformation of x multiplied with the phi transformation of z gives you back the original function. Now the question is, why are we doing this, right? The idea is to still think about this. If we had a linear problem, our dot product was fine, right? Linearly separable problem. If we had our data linearly separable, we could just take a dot product and that's it. The real problem is we don't have a linearly separable data. But if we have it, dot product is fine. Now we are assuming there exists a phi that can transform x and z into a different space, into a more complex space, where x and z will be linearly separable. Because if they are, then you can take a dot product to distinguish them. Of course, there is no guarantee that phi is going to solve your case. And that's why you have to try many, many different kernel functions before you can say, like, this kernel function works the best. But the point is, but there is another question then. Why I talk about this? I just talk about this phi. I find a phi, I do the transformation, I take the dot product, I'm done. Why bother about this? And they are essentially the same. Anybody on this, like, why do we care about it? Yes?
That might be like really inefficient to do the transform into the high dimensional space, but if you have like an equivalent one that's easy to compute, it'd be better?
Yes, so the answer is it might be inefficient. And that's true, because think about this. If x is a high dimensional vector, let's say 1000 dimensional vector. So x is x1, x2, x1000. And y is, or sorry, z. We have z here. So z is right? Now, you have to first do, if we are working with phi, you have to do this phi. Then you have to compute this phi. Then you have to compute a dot product. And it depends on how complex your phi is. You have to do all those things. But if you kind of simplify this process, you kind of compute a closed form function for this. You don't really need to do all those transformations first and then do the dot product. You could just directly compute what's going to come out of that. There is one more benefit that I'll tell you, but right now, this saves you computation, yes.
But even while finding the kernel, you need to do all the things that were told to be inefficient, right?
Yes, so not necessarily. Not necessarily. When you are told to compute a kernel, we will show you an example why this is easy. Okay, let me show you the example, and we will see why kernel saves us computation. Okay, and then again the definition is kernel between 2 points. I mean, a kernel function can be viewed as a legal definition of the inner product. So you have this kernel that can be, that is basically a dot product of a transformation of x and y, or x and z, the same transformation. And phi, there exists a phi which is kind of implicit, inner. This thing is happening not explicitly. This is something, if we compute k, that transformation, because k has the dot product and the transformation like molded inside it, right? We are directly going to compute k, and I'll show why that is more efficient. So the idea is to think about phi as implicit. You never need to know even what the phi is. But implicitly, that is what is happening. There is a phi that is transforming the data and taking a dot product. Okay? So here is an example. Okay? Let's see. So you see the first example in 2D space, right? So these are negative points, these are positive points. it's a circle that you need to define, or like an ellipse, you need to define to do the classification. So a line is not going to work. So there is no linear solution to this. So we are going to do some trick here, right? So you have, so the kernel here is defined as the polynomial kernel, which is the dot here, to the power d, right? Oh, this is a comma, but here we defined it as the dot product to the power d, right? Now, assuming that each x and z are n-dimensional vectors, right? They have to be equal. So x is x1, x2 till xn, okay? And z is also x1, x2, it's z1, right? z1, z2, zn. Okay? Now we define the simplest case, that n equals to 2 and d equals to 2. What happens here? So your x is just x1, x2, and z is just z1, z2, right? It's n, if we define n equals to 2, right? So your z, your kernel function in this case is essentially x1, x2 dot z1, z2 whole square, right? Just plugging in the values. Now if I take a dot product, that basically means x1, z1 plus x1, z2 plus x1, z1, sorry, x2, z1. Sorry, I'm making a mistake here. This is a dot product, right? x1, z1 plus x2, z2 whole square, right? Which is essentially x dot z whole square. Right? Now the question is, I know this is what we are defining as kernel, but what is the phi here? Because there must be an implicit phi that we should be able to infer that will transform both x and z, and if I take the dot product, that should also give me this. Right? What is that phi? I mean, we can try one phi from there. So one phi could be this: x1 square, x2 square, root 2, x1, x2. Right? Just assume that this is one phi. There exists a phi. We just define this phi. If we define this, then phi of z is also x1, not x1, it's a z1. z1 square, z2 square, root 2, z1, z2. Right? Now, we would agree that this phi is actually corresponding to this kernel function if I can show their dot product is actually equal to this. because this is what the kernel function defines originally, right? Whether this is a valid kernel, if I can use that phi to show that there exists at least one phi like that gives me this in the dot product, we are good. Question? Okay. So what we want to do is we want to compute the dot product, right? What is that? x1 square z1 square plus x2 square z2 square plus 2 x1 x2 z1 z2, right? Then what do we have? x1 z1 plus x2 z2 whole square, which is essentially x dot z whole square, right? Now the point is, if I now talking about the efficiency part, if I directly computed this two, I had to compute this, then I had to compute this, and this term, and then I had to compute all of this to come here, right? Do the transformation directly. But if I use the kernel function, I just compute this. I don't need to know what the phi was, right? Because eventually I'm computing this. This is telling me like there is an implicit phi like this that we are taking a dot product actually by directly computing this. This is where you just compute this part. You just compute this part and you forget this part. You don't even compute it. Is that clear? Okay. So, but things get more interesting. It's not just this efficiency. There is more. The point is the same K can give you multiple phis. And by computing the same K, just one K, you can simulate many different phis implicitly. It's not just one phi it captures. It captures multiple phis at the same time. That's where it's more interesting. So let's take another example. Let's take another example, not this one. Yes, let's take the second example. So we have this phi, right? Now let's think about another phi. So this phi is mapping x, which is x1 and x2, a 2D point into a 3D space, right? You have three different values, components. So this is a mapping that takes a 2D point into a 3D point. But think about another phi that takes you to a 4D space. And such an example is this. So think about phi of x is equal to x1 square, x2 square, x1, x2, and x2, x1. It's a 4-dimensional space, right? Phi of z. Why do I keep writing x? z1 square, z2 square, z1, z2, z2, z1. Right? Now take a dot product. Let's call it phi 2. x1 square, z1 square, x2 square, z2 square, x1, x2, z1, z2 plus x1, x2, z1, z2, which is essentially x dot z whole square. So now we get to the same kernel function with a different file. So now the beauty of the kernels is you can just compute this and internally it will consider both mappings at the same time to see which one linearly separates the data. And obviously there are many different combinations, as we will see. So if you have an n-dimensional vector and d-dimensional kernel, so the total number of features will be exponential that you can create. So with just d equals to 6 and n equals to 100, you get 1.6 billion terms. Now you see the power, like how many different combinations of features you are creating. Yes, we are not saying we are going to exactly create a feature for the hairstyle, but the hope is all those billion terms, some of them will capture it, or their combination will capture it in a linear way. All right? So now the question is, okay, we know kernels are great. How do I use them for classification? How do I use them in a perceptron, right? I had an original perceptron algorithm. That was very simple, but this looks complex. Actually, it's not. That's the point. So remember, this is still the perceptron algorithm, right? Anything new here? No. It's exactly the same update rules. You just need to replace the dot products wherever you have. You just need to replace the dot product with the kernel functions here. That's it. Remember, there is one interesting trick here. See, here we are updating the weight with a vector, right? I mean, with a data point. So there is a combination of weights and data point. But kernels only work with 2 points, right? The dot product is actually defining the plane itself, but it is in terms of 2 points. So that's why I earlier showed like weight is essentially a linear combination of points. So if you do a dot product of weight and a point, it's essentially a linear combination of dot product of points. Once you have a dot product of points, you can essentially replace these dot products between points with the kernel function of those 2 points. That's it. Once you replace the kernel function, it essentially transforms those data points into many different phi's implicitly and try to linearly classify. So the only change we need to make, wherever you see a dot product, replace that with this kernel function. That's it. Question? So you see, how do you predict? For prediction, instead of w dot t, we originally had w dot t, not t, it's x, right? Dot x is greater than or equals to 0. Instead of this, we are computing that formula, which is going over all the examples that we have seen previously with a new point, right? xi1 to xi t minus 1, that basically means up to this point, how many, whatever points we have seen, we're taking a dot product with, we are taking a dot product of their transform phi space with the transform phi space of X. One issue is immediate here. Yes, question?
Can you repeat what you just said?
What I'm saying is, this kernel function, each kernel, you see it's a linear combination of kernel function. That's clear, right? Now, each kernel function is essentially telling you there is a phi transformation that is transforming xi to some phi space and also the new point x to that space, and then taking a dot product, right? And based on that, but one issue is immediate here. What is that?
Is it that like some points will be in different spaces in other points?
We are transforming every point to that phi space. There is no point in the original space. Everything is now happening in phi space. We are just taking the real space, transforming into phi space, and we are just running the perceptron algorithm there. Nothing else is happening. Think about this. This w dot x was easy to compute, right? Now instead of that, dot product is looking like this. So it's computationally expensive. And it is looking at all the points that I have seen previously and in my training data set or something. So that basically means I need to go over my training data set multiple times. It becomes quadratic in computation. And that's why SVM does the same thing with kernels. And that's why these models are no longer popular today. Because deep learning is what? Is it quadratic? You are not supposed to know. I'm just throwing this out. What do you think deep learning is? The update rules. Why it's so popular? What do you think? What it should be?
Log in.
That would be great, but it's not. What's the next best?
And log in.
What's in between?
Linear.
Linear, n. So the updates of neural network is linear. This is quadratic. Login would be great. I mean, we don't have that. But okay, that's why SVMs are kind of forgotten because of the efficiency problems, because we have massive data now. And deep learning techniques are parallelizable as well as they're linear in time, so everything is faster. And we have GPUs to compute them even faster. And they can approximate any function. So all these things add up. Okay? Okay. So now the same theory still holds, right? If data is linear separable by a margin in the phi space, there is this if again. If it is actually linearly separable in the phi space, and remember phi could be multiple. All the possible phi, if at least one of them is helping, then with a minimum margin of gamma, the algorithm will converge by R divided by gamma square mistakes. It's the same, it's just everything is translated to the phi space. All right? Now the question is, okay, what are my options for kernel? Like, how do I know I have a good kernel? Well, the top one, which is called the linear kernel, what does it mean? If I use a linear kernel, is basically the dot product of 2 points. So if I use a linear kernel, what does that give us?
Same as perceptron.
Same as perceptron. That is the perceptron. Right? So we have actually learned perceptron with kernels already. It was just a linear kernel. It was not nonlinear. But you can replace linear kernels with this kind of more complex kernels, there are theoretical proofs that these are actually valid kernels because they can be shown, it can be proved, and some of them will be in your assignment. Like show a phi so that their dot product actually gives you this is a valid kernel. Right? So we already know this, like these are valid kernels. You can find a phi, at least one, such that the transformation of phi x and phi z and their dot product will give you these functions. There exists at least one phi. Okay? And there are some names also for those functions, that there are some standard kernels that people often try. They work pretty well for some data sets. So you have Gaussian kernel, you have polynomial kernel that we have already seen, you have Laplace kernel and so on. Okay? So now more like on a theoretical side of it, there is a theorem called Mercer theorem. You don't really need to know the proof for this course because I get complaints like this is getting too theoretical and we are computer scientists, we don't care about it. So, I don't even now remember what the derivation is, but the point is, here is a theorem we can believe that is well known in the literature. So K is a kernel. How do you know K is a kernel? K is a kernel if and only if. So you can think of K as a matrix, right? You have two-dimensional points and then some weights A1 and A2, and so the idea here is K is a kernel if and only if K is symmetric. So it has to be symmetric. And the second part of it is for any set of training points where you have x1 to xm, these are your training points, and for any a1 to am, so a1s are what? The weights, right? We have a positive semi-definite matrix. Yes? Question? No. So what it basically means is, yes?
Why are there the same number of weights as training points?
Sorry, what?
Why are there the same number of weights as training points?
Same number of weights as training points.
They're both to m.
Right. I mean, think about your perceptron. What did you do? For each point, you either added it fully, 1, -1 if negative, or 0 if no mistake. So each point comes with a weight. Right? In a perceptron, it's exactly the perceptron. Now, what this theorem is telling you is that as long as you have a matrix that is positive semi-definite with respect to this x and a1, like a's, that is a valid kernel. Okay? That is a valid kernel. I think I already talked about this. So it offers great modularity in that sense that you don't need to change the learning algorithm. You just replace the dot products with particular kernel functions. So essentially, you can go back to your perceptron code, what you have written in your assignment. You can replace that every dot product with a kernel function call, and you can actually have different kernel functions that you can call based on your some what is it called? What is it called when you have a website and you define some values that you want the website to follow? It's like a hyperparameter in machine learning, but I'm forgetting the name. But the whole idea is you have some configuration file, right? In a configuration file, you can define which kernel you want to use, and then you can write a code that will go to the perceptron algorithm and pick that kernel function to run instead of simple dot product. Okay? And then you can also mix and match algorithms with kernels. So it doesn't have to be a perceptron. It could be something else. But you could also, again, use a deep neural network with some kernel. Okay. So now we have kernels. They are great. And they are combining features of two different points, which is also great. So we are mixing high dimensional features of two different data points. But what about mixing two kernels themselves? We should get even more powerful kernels, right? If we can do that. Because kernels are already mixing high dimensional features and giving us more opportunity to define a plane that linearly separates the data point. If we could combine kernels into another kernel, that could be even more powerful. So that's, and there are, fortunately, there are properties of kernel functions that we can leverage to create new kernel functions. Okay? So that's what we are going to show now. So the first one is the closure property, right? So the linear combination of two kernels is still a kernel. That's the theorem. So what we are basically saying, if you have a kernel K1 and another kernel K2, if we know they are valid kernels, then they are linear combinations. So C1 times K1 xz and C2 times K2 xz. This is a valid kernel. And now we will see why. Okay? So we have to, how do we show that this is a valid kernel? We have to show that there exists a phi. There exists a phi that transforms x and z into such space, and if we take the dot product, we'll get this kernel, right? But we already know, like, this is a valid kernel. So there exists at least one phi 1. We know that, right, by definition. This is a valid kernel as well. So there exists a phi 2. Yes?
C1 and C2 are just constant.
Yes. It's a linear combination. It's like a weight. Right? So you have phi 1 and phi 2 for sure. Now our goal is to show that there exists a phi that if we transform phi with x and z, we'll get k, given that we already have valid k1, k2, and phi 1, phi 2. Okay? What do we do? Let's try this phi. And the idea is to use something like this. It's a concatenation. It's a concatenation of two phis. So we are basically saying this phi is a concatenation. It's a higher dimensional space. We are concatenating features. If we assume this, we could prove that. Because then phi of z is going to be the same right? We're just showing, you just need to show one phi that works, and we are good. Now you take a dot product of these two. Phi x dot phi z is essentially C1 phi 1 x phi 1 z plus C2 phi 2x phi 2z, right? But what is this by definition? This is a dot product of phi 1s of two data points. What does that mean?
Kernel 1.
That is kernel 1, yes. So C1 K1 xz C2, what is this?
Kernel 2.
Kernel 2 xz, which is exactly the same as this. So which is equal to k of xz. That means there exists a phi that such that the dot product of phi x and phi z gives you k of xz. So this one is a valid kernel. Question? Yes.
Like, is there any guarantee that it's going to get better performance if you concatenate these kernels?
There is no guarantee. There is only one guarantee, that no model is perfect. That is guaranteed. And then how do you find the best model for your case is where you run experiments and see what works. Because you are dealing with something where you don't even know how things work. You are trying to figure that out. So in order to find out how things work, you need to assume many, many different ways of how things work and see which one actually fits.
So just the accuracy is the parameter that we decide if a kernel is efficient or not.
You can have more metrics. I mean, we have seen metrics like precision. We have seen metrics like recall. Whatever your metric is, maybe your metric is if you are deploying this in a company and you have like revenues generating, right? You run it for a month and see whether your revenue has increased or not. It depends what your goal is. Maybe you want to increase traffic to your website. You are counting the number of people that are logging on. That is your metric. If that improves, yes, that is helpful. Right? Okay. The second one. So we have said, like, again, the second property is if you have two kernels again, and if you define a new kernel K, which is essentially a product of the two kernels, that is again a valid kernel. So in exams, we might ask you, so here is a kernel, here is another kernel, exact instance of that, and show us that their multiplication is a valid kernel, right? Or their linear combination is a valid kernel. You just need to find a phi that works. Okay, so previously what we defined as phi was concatenation of the weighted phis. We did a concatenation. But now we are not going to do concatenation. We are going to do multiplication. So that's what will give us a valid kernel. That's what will help us to show that this is a valid kernel. So what we define is this. So phi of x is essentially the dot product of phi 1 of x and phi 2 j of x. Right? So it's essentially saying you have a phi 1 of x dot phi 2 of x. We are saying, because there is a phi 1 and phi 2 we know, and then phi of x is essentially the dot product, which means a dot product over all these combinations. So what you write is, if you do a dot product, what we get is something like this. I of x, phi 2, j of x, phi 1 I of z, phi 2 j of z. And this is the dot product of x and z. We are just multiplying this term twice, one for x, one for z. Okay? But what we can do here is, we can play with this indexes, and we can say this, and we take the I here, we will switch the I with the j, and sorry, this is the I, and there is a j of x. Phi 1 and phi 2 was here, so this is, sorry, this is 1, this is 2. We are just playing with the indexes of the multiplication. The whole idea is to like capture this and capture this, because that's our goal. We need to show that we have the multiplication of these two kernels. We are trying to show this. So this one is actually phi 2 of x and z. We are multiplying the transform space. So that is essentially K2. K2 xz. But now this K2 xz doesn't depend on I, so it's a constant. We can bring it forward. So it's a K2 xz. Then this part is essentially the dot product in the phi 1 space, which is just K1 xz. So now we have shown that phi of x, which is essentially the dot product of phi 1 and phi 2, phi x, which is essentially the dot product of, so you have, what we have defined is essentially the phi of x is essentially the dot product of phi 1x and phi 1z, and if we take multiplication over two different data points, you have a kernel that you can generate in that dot product space. So So if we can show like this product, which is defined as the k of x and z, as a dot product between the phi space transformation of x and z, then we would say this is a valid kernel. So let me go over it one more time. I think it has a little kind of, it can be a little confusing in terms of the notation. So let's start from the beginning again. So you have K1 and K2. These are two valid kernels. What you are doing is, we are just multiplying these two kernels, and we are saying this is a valid kernel. The way we are going to do this is by saying that phi of x is essentially all the terms that you get by enumerating over I equals to 1 to n and j equals to 1 to m. Right? And what you are going to do is essentially phi, and then of 1 means the phi first function over transformation of x. So each term of phi, and you also have each term of phi 2. You kind of take their element wise product. Right? All of them. So it's a little confusing, I can see, in terms of the definition, because if you kind of enumerate over all the possible i's and j's, you get one. Yeah, it's a set of values, but it's not apparent if you just have a first bracket. I'll try to see how I can improve the slide. Yeah. It's basically many different combinations of phi 1 and phi 2 that should be there. It's not apparent from this kind of first bracket notation. I'll try to update this, but the whole idea is you have element-wise product of phi 1 and phi 2. And then if you take a dot product between these two vectors, it's essentially vector, right? So then you get these 4 element chunks in terms of index over I and j. And then you can kind of bin them with respect to, you can group the phi 2s together and phi 1s together. Then phi 2 will boil down to K2 and phi 1s will boil down to K1. Okay? All right. So, if we come back to the discussion, like how kernels are helping us. The point is, whenever you have an algorithm where you take dot product and make a decision, or like make a following step, you are essentially doing element-wise product and a sum. The good thing with kernel is, now you can do the same thing with that kernel function. You replace the dot product with that kernel function. You are essentially simulating many different dot products at many different transform space at the same time. So that is a significant performance boost in terms of what are the possible like solutions you are exploring, but still that is quadratic because your weight updates are still dependent on weights of each point. So whenever you have a new point, you have to compute dot products with all the previous points, and that means it will be quadratic in nature. So it doesn't scale very well. At least it used to scale and work pretty well until we were like 2010, 2012. That basically means the data set was not that big at that moment. Whatever data we used to work with was fine for quadratic complexity. But then our data set has grown like crazy. And our computation power has increased a lot. So quadratic computations, although our computation power has increased a lot, but the data set explosion is much bigger than that. So essentially, n square, we cannot afford n square algorithms today. But we can still teach them in the classes and give you assignments with smaller data sets that can still work. Okay? And it's good to know how things changed over, because even if you go 10 years back, like kernels were the thing. SVMs were the thing to do. Okay? Right, so lots of machine learning algorithms are kernelizable, right? So you can kernelize perceptrons, kernelize SVMs, which we are going to learn in the next class. You can kernelize even linear regression. Remember? In a linear regression, what do you have? You are essentially computing some weights, and then you are multiplying with those weights to make a linear decision. So you have a dot product kind of thing there as well. You can kernelize that. And there is a clustering method where we also do this kind of dot product for similarity. You can also kernelize that. But I don't know if I will get time to go over clustering in this course. It will depend on how things evolve, but that is also something you can kernelize. So almost a lot of things. I don't think I have anything more here. Yeah, the question was, how do I choose a kernel? And that's where kernels often, if you look at this, kernels often encode domain knowledge. So people working on a particular problem for a long time, they know their data very well. And they have been experimenting with this, so they know which kind of kernels are better for their problem. So it just evolves with experience, right? There is no clear-cut answer. The other way to figure out is to try different kernels. And also for each kernel, you have some hyperparameter. For example, in the Gaussian kernel, there is a sigma. You can assume a constant sigma, or you can try to fit which sigma you want to figure out. So the idea is to do cross-validation. So we know what cross-validation is, right? You have some training data, which is split into training and validation set. The testing data is held out. And then you try different values of sigma to learn on that training data set and see what accuracies you get on the validation set. And based on some validation numbers on different partitions, you can choose which sigma should be chosen, like which is the best one. Okay? So there is a good amount of trial and error that you need to do with any machine learning model that has any hyperparameter. That is something unfortunate, but that is something you have to do. Otherwise we would have a perfect closed form mathematical formula to solve it. We don't have that. That's why we are doing this empirically in terms of computing, right? Otherwise we didn't even probably need machine learning. I mean, the statistics course was fine. Okay, so if you don't have anything else, I'll stop here. And I have some announcements to make, which is, I don't know if you have seen this, I have got rid of one assignment in the schedule. So that means we are not going to have 8, not going to have 0 to 9, but we'll have 8. And so it also means there are 2 more assignments pending. Okay? So one will be related to this kernels and support vector machine, and the other one will be related to neural networks. And I want your feedback in terms of what you want to see in the neural network part, because the implementation itself is going to take time. Now, given your experience now and what you want to do in the next month, do you want to see more like a theoretical assignment on, like conceptual assignment on neural networks, or do you also want to implement neural networks from scratch? I see one nodding of head clear, but yeah, I need to hear from more people. No? Okay. Should I make it a bonus kind of thing, like people who implement this like it? So the conceptual part becomes the conceptual part becomes mandatory. The implementation part becomes bonus. And if you do a good job in the bonus, I can replace that with your worst performing assignment. Does that help? Or I can supplement that to your project score if that is not perfect. Well, I can supplement that to boost your grade in any way. Does that sound good? All right, so let's do that. So we'll keep that bonus. If you are already doing pretty well, probably you don't need to. Well, if you are doing well, then you should be liking to do more. I mean, it's a paradox, but if you're not doing well, then you need to try work hard and do that to get more points. All right? See you next week.